the or not deep into the various other techniques. One of them is squeeze theorem. Okay, so using the squeeze theorem, squeeze or sandwich. So what does it say is, if there are three sequences, an, bn, cn, such that an is always less than or equals to the bn less than or equals to the cn for all n. That means a1 is less than or equals to b1, which is less than or equals to c1. So it differs by n, but this relation is maintained for the same n. If an converges to a finite limit, let's say it converges to 0, cn is also converges to the 0, then bn must converges to the 0. That's the theorem. So it looks like this. If we draw some graphical evidence, see, this is the an is less than, right? So let's make it an like this. This is the an curve, and cn is, you can imagine, this is just an example, very simple. These two curves cn and an grazes the 0. This is y is equals to 0 line. So then our bn, which may look like this, for example, if it is, so this curve is sandwiched, you can make it even. So you can see that the cn curve is sandwiched between an and bn curve is sandwiched between an and cn. This is an, this is cn. Okay, so that's the theorem. So whenever, if it is not possible to find the limit of the sequence using the L'Hopital's rule and other basic techniques, then you use the help of the squeeze theorem. So for an example, if you want to look at that, okay, we'll do some examples here. So the first one is like this. So n factorial by n to the power of n. So this is the sequence we have. So limit, if you want to find the limit n tends to infinity, n factorial by n to the power of n. Here you can see, as n tends to infinity, this factorial is tending towards, n factorial is tending towards infinity, n to the power of n is also tending towards infinity. So we doesn't know, so infinity by infinity form, we are not sure about infinity power infinity. So we can't use the L'Hopital's rule here, because you cannot differentiate this one. So L'Hopital's rule is not useful here. So what is the next thing is, we'll make use of this one. Okay, so for any n factorial by n to the power of n, for any n, this is always greater than 0. Okay, this is always greater than or equal to 0. You can put this equality sign, but this is never gonna be okay 0 though. for any n factorial. You can make sure that this is 0 what do you say this? Okay. Okay. Take 4 for the n. 4 factorial by 4 to the power of 4 is never gonna be 0 there. So we analyze, so we have found the sequence which is bounded below, that is 0 sequence, a constant sequence. This is a sequence which contains only 0 0 0 0. Okay, such sequences are called constant sequence. This converges to the 0 only. Then if you observe, to find the upper limit of the sequence, if you observe this n factorial by n, if you analyze this, n factorial is nothing but n into n minus 1 into n minus 2. It will go up to 3 into 2 into 1 divided by, okay, n to the power of n here, n into n into n into up to so on, n into n into n. So for each and every term there is one n here, so we can cancel out the first terms in the numerator and denominator since they are equal, and then the remaining term we can estimate this. See this, n minus 1 by n. For any n, this term is always less than or equals to 1. So even this one is also, this term is also is less than or equals to 1. If we continue going, this term is also less than or equals to 1. This one is also less than or equals to 1. So product of all the numbers which are less than 1 will be a less than 1. Less than or equals to, no, you cannot say equality. Okay, so it is strictly less than 1, right? So here the 1 by n is multiplied by a number less than 1. So the outcome of this product will be a number which is less than 1 by n, right? So our upper limit is also found here. So n factorial by n to the power of n is less than 1 by n, which is greater than or equals to 0. You can keep the equality sign here, but there is no harm. So if you can see that this is a 0 sequence, this is a 0 sequence which converges to the 0. This is 1 by n sequence, 1 by n, as n tends to infinity, this is also converges to the 0. So the n factorial by n to the power of n is sandwiched between these two, must converges to the 0. So we can conclude that this, the sequence n factorial by n to the power of n converges to 0. Okay, we will take another example here. If you see another example which okay, and let's take the second one. The sequence sin n into sin 1 by n. Okay, so this is the sequence which converges to the 0. Sorry, that to check whether this sequence is convergent or not. To know what it is, to find the upper limit and the lower limit, we need to know some basics of the trigonometry. of the sine function. So the trigonometric sine function, sine value, sine x, its modulus is always less than or equals to the x, or x, you can say this. And another is sine x range is bounded by 1. So from this inequality you can have sine x is less than or equals to the x is greater than or equals to minus x. From the second inequality, sine x is less than or equals to 1, greater than or equals to minus 1, right? So we now examine the our given question here. So first we take the first term, sine n. Sine n is lies between 1, its value lies between 1 and minus 1, using this one, okay, that inequality. So when sine 1 by n, and as n tends to infinity, that means n is always positive. So this one is, for these values sine is always positive. If you so we can directly multiply here, so it becomes sine 1 by n, and this is less than or equals to, if sign is negative, this inequality signs will change to the reverse direction. Sine n into sine 1 by n is less than or equals to sine 1 by n. So as we know, we use another equality. This is the first equality we use here. So by this you can keep this as in mind. Sine x is always less than or equals to x. So sine 1 by n is less than or equals to 1 by n. If you keep this inequality in mind, so you can say that sine x is always less than or equals to minus x. So you can write minus sine 1 by n is always greater than or equals to minus 1 by n. So this is the given sequence. So we obtain sine n, sine 1 by n is, which is always greater than or equals to 1 by n, less than or equals minus 1 by n, less than or equals to 1 by n. So we obtain this inequality. If we observe here, 1 by minus 1 by n converges to the 0, 1 by n is also converges to the 0, so this must converges to 0 by the squeeze theorem. Okay, so the sequence sine n, sine 1 by n converges to 0. So this is using the squeeze theorem. For suppose if you want to find using the limit finding techniques, limit n tends to infinity sine n into sine 1 by n, as n tends to infinity, this is sine 1 by n, sine n. So you can say, you can make the limit n tends to infinity sine n, limit n tends to infinity sine 1 by n. This is possible, we can split this limit up here, because we have the definite limits here. That means not definite, we know what are these here. As n tends to infinity, sine 1 by n becomes sine 0, which is 0. Okay, for suppose here, as n tends to infinity, So sign value is bounded by the range -1 and 1. Okay, so this is the any value L, that L is in between 1 and -1, which is a finite value. Any finite value is multiplied by 0, that gives the 0. Okay, so even you find in that sense also. So you can say that the sequence converges to the 0. For using the squeeze theorem, there are two more problems, but I am at to find the answer for them. I am at to reason them. So I'll skip those two here, but you can see we use the another technique, that is a monotone convergence theorem. The other technique which I left here, that is the monotone convergence theorem. Okay, so monotone convergence theorem, when, for suppose, if you want to check whether a sequence is convergent or divergent, and if you are no need to find the limit of the sequence, then this theorem is used. So for suppose you can prove a sequence which is monotonically increasing and it is bounded above, then you can say that such sequence is convergent. For a sequence is monotonically decreasing and which is bounded below, you can say that such sequence is also convergent. Otherwise, a monotonically increasing sequence which does not have a upper bound is divergence to the infinity. A monotonically decreasing sequence which does not have the lower bound, so it diverges to the negative infinity. You can say that. So one of the, we'll see some of the examples here in this. The main use of this theorem to know whether a sequence is convergent or divergent. Okay, but it does not recommend explicitly the limit of the convergence. If you want to find the limit of the convergence, you make use of either squeeze theorem or the L'Hopital's rule or basic finding limit techniques. For example, here, for suppose, see here, a, and this is given by the recursive relation, square root of 2 into an minus 1. Okay, for all n is greater than 1, and a1 is given as 2. So we find a2 is nothing but 2 into a1, that is square root of 2 into 2, that is 2. So a3 is also you will get 2, a4 you will get 2. So this becomes a constant sequence of 2 which converges to the 2. Okay, so we unable to use the monotone convergence theorem here. We take the same recursive relation 2 into an minus 1 for all n greater than 1, but I change here a1 is equals to 1. This is what I change here. Then a2 is square root of 2 into a1, that is a1 is 1, so it becomes square root of 2. a3 is square root of 2 into a2, so this becomes square root of 2 into a2 is nothing but square root of 2. So for a3 there are 2 for a1. So for suppose if you want to find a5, it becomes square root of 2, square root of 2, 4 2's will come, 2 square root of 2. Okay, like this it's going. See here, you can find the upper limit, and so we can see this here. See, this is see 2 root 2. A1 is 1, a1 is 1, a2 is root 2. So a2 is greater than 1. This value approximately equals to 1.414. Okay, here 2 is multiplied by a number which is greater than 1. So this number is increased further, and take the square root of it, which will be greater than root 2 itself. So this is nothing but a2. So a3 is greater than a2. If this continues, assume that an minus 1 is less than an. So you multiply both of them by 2. Since both are positive here, you can take the square root. This is nothing but an, and this is nothing but an plus 1. So by the assumption, see here, we see by what do you say that by induction theorem, see a2 is greater than a1, a3 is greater than a2, and so on. It is increasing by assuming that this an is greater than an minus 1. We are able to prove an plus 1 is greater than an. So this identity holds. By this, you can say that the given sequence is monotonically increasing sequence. So for now, we need to show that it is bounded above. To show that it is bounded above, so what is a1 is 1. So this one is less than 2. What is a2? It is square root of 2, which is less than 2. The a3 is square root of 2 into root 2, which is less than 2. How do we know this one? For suppose, let's see if this holds. 2 is greater than square root of 2 root 2. Squaring on both sides, you will get 4 is greater than 2 root 2. So you can divide with the 2. It gives you 2 root 2. You know this value 1.414. So this holds. So I am proposing here that 2 is the upper limit of this sequence. For suppose an is less than 2, assuming if the same pattern is continued, then you multiply both of them by 2. 2 into 2, 2 an. So this becomes 2 square. Take the square root for both of them. Square root of 2 into 2 is 2, which is greater than an plus 1. So this holds by the mathematical induction. What is this means? See, if this pattern continues here, you assume this statement. You seen that this pattern continues. You assumed for any, and what do you say that for any what do you say that for any general term, then we proved this is true for the next term next term also. So this pattern continues. That logical reasoning is called mathematical induction. Okay, mathematical induction. So our sequence is bounded above by 2. So a monotonically increasing sequence which is bounded above is convergent. So we know that it is convergent to a finite limit L. That means limit n tends to infinity, an is equals to the L. We can see limit n tends to infinity, an plus 1 is also L. As n tends to infinity, next term we take an plus 1 is also tends to the L. So we can take 2 into an in terms of limit n tends to infinity. For this one is square, this is square root of 2 into an. So this becomes 2 into limit n tends to infinity, an is equals to L. This is nothing but L. Square root of 2L is L. That means 2L is L square. You can see here. Okay, when you from here you can say that 2L minus L square is 0. You take the factor out L. 2 minus L is 0, which shows either L is 0 or L is equals to 2. L cannot be equals to 0. Why? Because you can see that it is monotonically increasing and first term itself is 1. First term an itself is 1 and it is monotonically increasing sequence. You can what do you say that that limit cannot be 0, but limit is 2. So you can say that this sequence is monotonically increasing. Okay, the sequences converges to the 2. So up to here our work is done. So we've shown using the monotone convergence theorem, we've shown that this sequence, the given recursive related sequence, converges using the monotone convergence theorem. And from here, this is the additional work we did. How to find, if we know that sequence is convergent, then how to find that. This technique is used extensively when we know some sequence is convergent. Okay, so we proved that sequences converges to the 2. Right, this is the use of the monotone convergence theorem. So we see some other example which is given in your textbook, which is a critical. So I will make that easy as possible as I can. If you understand that, then see there are that not only is, for suppose a sequence is given like this: an plus 1 is equals to an by 2 plus 1 by 2 into an for all if I decrease to 41 by 40, and it is further decreased to 3281 by 8. See here, there is only one difference here. So you can say that the sequence is converging to 2, as if we can see that without any mathematical proofs. You can conclude that, see, even if this number gets bigger and bigger and the denominator is 1 less than that of numerator, so the sequence is will be like this. If you can, the first term is 2, from here the it is 1. You can see that the sequence is converges to the 1 like this, without any mathematical evidence. You can see that. But if you want to prove that mathematically, then that's another question entirely. First, we show that this sequence is bounded below here. So the general term given, an is nothing but, an plus 1 is nothing but an by 2 . So we have an plus 1 is nothing but an by 2 plus 1 by 2 into an. If you take 2an as the denominator, the numerator becomes an square plus 1, right? Okay, keep that as in mind. But you see here, for any real number which is squared is always greater than or equals to 0, right? For any real number which is squared is always greater than or equals to 0. So in that real number sense, I will what do you say, I will substitute an minus 1. Okay, this is because I know the proof, but to make it as simple as that, okay, I will show you how I did arrive to that understanding. But square of a number is always greater than or equals to 0. Then if you square it, it becomes an square minus 2an plus 1 is always greater than or equals to 0. So an square plus 1 is always greater than or equals to 2an. So if we divide this entire inequality by 2an, it becomes an square plus 1 by 2an is always greater than or equals to 1. So our sequence is bounded below by 1, and you can say it is monotonically decreasing sequence by the values, so which is bounded below by 1. So we proved that, and now we prove its a monotonic decrement. For that, as you can see that you are assuming a1, you can see you observe this one, a2 is greater than a3, it is monotonically decreasing, and so on. And then if this sequence is continuous and if this is true, if this sequence and if this is true, we need to show that an is greater than an plus 1, right? So to show that, we know each an is monotonically, that means is bounded below by 1, right? So we can have, okay, an square is also, can say that it is greater than or equals to 1 if you add an square plus an square, you add an square to this inequality, 1 plus an square, so it becomes 2an square, which is greater than or equals to 1 plus an square. So this one, you divide the entire inequality by 2an, so it becomes like what remains is here is an, which is greater than or equals to 1 plus an square by 2an, which is equals to an plus 1. So we see that an is greater than or equals to an plus 1. So we shown that it is monotonically decreasing, and we already shown that it is bounded below by 1. Bounded below by 1. So what does it says is it is convergent. To find its limit of convergence is another matter. So for suppose if we assume that limit n tends to infinity, an is L, so does an plus 1. This is also converges to the L, but an plus 1 is an square plus 1 by 2an, that is equals to L. This limit we get here is L square plus 1 by 2L is L. So we have L square plus 1 is 2L square. So we have L square is equals to 1. L is plus or minus 1. So as L cannot be negative 1, so that implies L must be equals to the 1. So the above sequence is converges to the 1. So the given sequence an converges to 1. So we use the monotonic convergence theorem in this sense. Okay, for suppose if you are not sure in a competitive exam, if you are sure that it is convergent by just observing the sequence whether it is decreasing, all these calculations, see where monotonically decreasing and it is bounded below, you no need to logically or mathematically arrive to this proof, but you can see that by general sense you can see that whether it is monotonically decreasing or and it has a bound, whether it is bounded below or above, you can sense that. If you did, you can directly come to this. Okay, you can directly perform this step to find its limit of convergence. So that's how we do deal with the sequences. So next on, why? Because I stress so much on the sequence is that a series is also the having the same has the same behavior. Okay, if we I will give you a general glimpse of what does the series is, that we are given with a numbers. The series is like it is given, it will be given like this an, where n is equals to 1 to infinity. This is the symbol of the summation. This is the symbol of the summation. Okay, so this is the general term, n goes from 1 to infinity. So a series is nothing but a sum of infinite terms of the numbers a1 plus a2 plus a3 plus a4 plus and so on. It uh, so a series, how does a series is related to sequence is we take the finite sums. So first term we will take a1. Let's say we define a sequence like this. b2 is a1 plus a2. b3 is, we define like this, a1 plus a2 plus a3, okay, and so on. We define bn is a1 plus a2 plus up to so on, summation up to n. So you can define something like this: some k is equals to 1 to n ak, right? So the now we do some medical examination here. The sequence bn and the series an has the same behavior. If this one diverges to plus, if this one converges to a finite limit L, then this is also converges to the L. If this diverges to infinity, the series also diverges to the infinity, diverges to minus infinity, or it oscillates, it is also oscillates. Okay, so this happens. That's how important the sequence in regarding the series perspective, because the entire behavior of a series is examined by the sequence. You can say this is sequence of partial sums. This sequence is called sequence of partial sums, right? This is a partial sum. You take the part of a greater sum, right? So this is how it is related as a basic definition, but we have some more advanced technique how to find easily the sequence, the series values and all. We have some more advanced technique than examining the sequence of partial sums, but the basic approach is this. Examining the sequence of partial sums is the basic approach, but there are some more easy and some of the advanced techniques are there to know the nature of the series. So if we get perfected in the sequence, the series also becomes very easy to us. Okay, so with that I conclude here. See you, Tony, next time.